All right. So let's go back to that 3-3 problem on trig substitution. All right, so we're going to take a look at this one right here. Let's see, if we graph this right here, rough sketch, it's not a pen. And anytime you do a volume problem, you got to do some kind of rough sketch for it. So get it started in something like Desmos or GeoGebra or whatever your graphing thing is. And then, so this function goes something like that. It's got this kind of bell type shape. It's asymptotic out this way. And this thing is going to peak at y equals 1/9 when x is 0. And so let's say that's about 1 right there, and maybe 5 is about right there. And so I'm taking this region right there and revolving it around the x-axis, is what I was asked to do here. So when I do that, I'm going to get this 3D shape that looks kind of like a funnel. And so I have to decide, do I want to use washers here, or do I want to use discs? Shells or discs. And yeah, looking at it, a shell is pretty easy here. A disc, excuse me. A disc is pretty easy here because it just has that function on top and the y-axis underneath. So dx, and then the radius here is just my function. Right, the distance from the axis of rotation up to that top curve. And then the formula for disks or washers, so I'm going to make a note, I'm using the disk method, is the integral of pi r squared dx as x goes from wherever to wherever. So I think, especially on the real written test you take later, the proctored one, I highly recommend you draw your picture, you think about washers and disks, maybe sketch each out, and then make a note of which method you're going to use and what the general formula looks like. And then start to identify what pieces you need from the graph. Write everything down. The more you write down, it frees your brain to make sure you're doing it right. So I think we've clearly established what R is here. So then we just write it out. So now I have the integral as x goes from 1 to 5. I can pull the pi out. And then I have parentheses 1 over 9 plus x squared dx. And we could either use partial fractions on this, or we could use trig substitution. And oh, you guys brought lunch. Nice. I don't know which one is easier, but I'm going to go over the trig substitution version. If you wanted to do partial fractions, recall that if your denominator is an irreducible quadratic, then the partial fraction version of it is going to have a linear factor in the top. And our complication here is we have that sucker squared, right? So I could rewrite that as 1 over x squared plus 9 squared. And the partial fraction version of that would be ax, I should do the capital AX to be consistent, plus b over x squared plus 9 plus cx plus d over x squared plus 9 squared, if you wanted to try the partial fractions version. So that would be the setup for that one. I'm going to set up the trig version and get it started and let you guys go as you wish. So, so right now I have 1 over x squared plus 9 squared to think about in terms of trig substitution. And for trig substitution, what matters is basically whether you have a plus or a minus in between and whether x falls on one side or the other for the minus. This is a plus, which means that that's related to the hypotenuse. Now, because of the Pythagorean theorem, we would end up with the square root of x squared plus 9. So you don't have to artificially insert it into the problem we started with, Carter. It's just when we write the triangle, it's going to be there. Because then if that were the hypotenuse, then x would have to be there and 3 would have to be there. So that this doesn't perfectly match my problem, it's no big one. Okay. So then what do? Well, what trig function is the easiest to form based on this triangle?
Tangent.
Tangent, yeah. So then we get the substitution that x equals 3 times the tangent of theta, which gives me dx, 3 times the secant squared of theta, d theta. Let's see, how do I incorporate the square root? What's the easiest function that involves the square root?
Cosine.
Sine. No.
It's either cosine or secant. You can take your pick.
Secant.
Secant. So if we choose secant, then this would tell me that the square root of x squared plus 9 would be equal to 3 times the secant of theta. And how do we get rid of the square root?
Square.
Square both sides. So x squared plus 9 must be equal to 9 secant squared of theta. And now we have everything we need for the substitution. And I'll leave you guys to confirm that and see what happens. Okay, sorry, my notes right away there. Let's see. Okay, Daphne and Samuel. All right, so enjoy, have fun with that one. Check out the partial fractions if you're feeling brave and adventurous this weekend. All right, next problem. This was number 25 from homework, was it 2.6? Let's see, where did that come from? Homework 2.5. Number 25. So, a couple things to think about. Let's see what they've got. If the force is variable, you have to use calculus. You can't just say it's work ton distance. Okay? Is this a variable force?
Yes.
Yeah, because it says the force depends on the distance, and over here, inside it says the distance is going to change. So I have to use calculus to do this. Okay? So ultimately, let's say x is distance, then my work is going to be the integral from whatever x value we start at to whatever x value we end at. I'll deal with that in just a minute. Of the force functions, my function happens to be k over x squared. I'm going to figure out what k is. That's force. Where am I going to get distance from?
Dx.
Dx is the distance in this case, correct? Okay. And in some work problems, dx is part of the force. In other work problems, it's the distance. It kind of depends on the problem. In this case, since x is part of the force, then dx gets to be the distance. And you always got to stop and think about, where's my force, where's my distance? Okay. So in order to do this, we got to figure out a couple of things. What x value should we start and end with? And in this case, because they gave me a partially formed function, I need to figure out what k is. But they gave me enough information to find that. So to find k here, the given information is that suppose when magnets are 6.6 meters apart, the force is 3 newtons. So they're giving me the distance and the force so I can find k there. So let's do that. Let's see, pen. Let's go with red. So let's see, when the force is 3 newtons, I don't know k, but I know the distance is 0.06 meters. Do newtons and meters work well together?
Yes.
Okay, what if this was newtons and centimeters?
Change it to meters.
We'd want to change it to meters, so keep that in mind. All right, so solving this, I get k is equal to 3 times whatever that is. 0.06 squared.
It's 0.0108.
What does it end up being?
0.0108.
0.108?
Yeah.
Is that right?
Okay.
And sometimes in problems like this, I just leave k in this form, hoping some of that might cancel later. But either way. All right, so let's see. So that's our k, so that's going to go right here in a minute. Next, find the work in joules. Joules is a Newton meter. Okay, so we're working with newtons, and we're working with meters there. And the distance we have to move is also in meters. So I think we're looking good. The distance, let's see, that is required to move the magnets from a distance of 0.02 apart to 0.1, right? So this is going to be 0.02, and that's meters, which is good for my final answer. And this would be 0.1, which is good for my final answer. And again, the setup is the hardest part of this. So here's what I think I have on a new page. Ooh, wrong button. There we go. I think that the work is going to be found in this case by integrating as x goes from 0.02 meters to 1/10 of a meter, 0.0108 for k over x squared dx. And I think you guys got it from there. That was fun. Questions? Okay. Ooh. We also have an excellent jump start on the take-home exam. Yes, Scott.
So you don't have to answer this if it's like too early, but
Yeah.
could you pull out the k since it's just a
Yeah, k is just a constant. We just pull that out. Yeah.
Okay.
Yeah. So the next, this is a good question, but always my next step once I get the initial setup is how can I rewrite that to make the antiderivative as easy to find as possible. So my routine would be to pull out the constants
Then you just have to find the antiderivative.
and then rewrite that as x to the negative 2, and then go from there. Yeah. So how can I make my life as easy as possible? And be careful, like assure yourself that, yeah, I can't pull out the constant in this case. Like, don't do, and that's just factoring, that's just algebra. So try not to do illegal algebra. How could you check if that was an okay thing to do?
Take the derivative.
Take the derivative, okay. What else?
Plug in the numbers you gave before.
Plug it into what? Integral calculator, yeah, do Desmos or GeoGebra has that calculate the integral function. Yeah, use some technology to help you figure it out, double check stuff. Okay, what shall we do next? I was thinking we needed to try another improper integral.
Can you go to like the last one for improper integrals? Or the second to last one? So,
In this section?
yes.
Yeah.
It look funny. Sound funny.
Last or second to last?
Wait, yes, that one.
That one right there? This one right here. Okay. Yeah, let's
Like-
try this
Yeah,
one here.
that.
All right, zoom in on that one a little bit. The Laplace transform of a continuous function over the interval. So those of you who are wondering what the heck a Laplace transform is, it's an integral function. That's a Laplace transform. Why would you care? Well, if you go into engineering, you will see Laplace transforms, I guarantee it, in your future.
So is it just a method or is it just a...
So you know how we did trig substitution to be able to come up with an antiderivative? Laplace transforms are a similar thing. They're a way to come up with a new function based on your old one that's easier to work with in some context. Yeah. Trying to think of another example of when it's kind of like it's a substitution that makes our life easier. If you're a science fiction fan, Laplace transforms take you into an alternate dimension where the rules of reality are slightly different. So I can do like Superman type stuff in this Laplace transform dimension. Is another way to think about it. All right, so Laplace transform says, given some function f of x, if you multiply it by e to the negative sx, where s is something, your new variable, then you get this other function. The interesting thing about a Laplace transform is it is an improper integral, which means a limit is involved in taking it. So we want to do that here for the function x equals e to the 8x. So it's easier than it looks. Just have to plug in and see what happens. I'm going to copy, let's see. I only need this top line and then that last line. Okay, let's do it. Let's do it in blue today. So here I'm just told let f of x be e to the 8x, so I just plug in. My new function, capital F of s, is my variable. So you know how like we do u substitutions? We could say this is like an s substitution kind of. Is going to be equal to the integral from 0 to infinity of e to the negative sx times our new function e to the 8x dx. In order to pull this off, I'm going to replace infinity with a variable. Usually we use b, and then eventually take the limit. So I want to do the integral from 0 to b. And let's see, before I do that, this actually cleans up a little bit algebraically. I have the same base, right? So then I add the exponents together.
Mm-hmm.
So then this just becomes e to the power negative sx plus 8x dx.
Okay.
Right, so anywhere I can do algebra to make the integrand simpler is a good idea. And actually, even I could even rewrite it one more time. I could factor an x out of there, which might be helpful. I'm going to rewrite this one more time. Integral from 0 to b of e to the power. I'm also going to change the order. So e to the power 8 minus s x dx. I have to do that? No, but it'll make defining the antiderivative easier. All right, what's an antiderivative for e to some power?
1 over whatever's inside.
Yeah, it's 1 over whatever that multiple is times e to that power. Yeah, so an antiderivative here, new page, again, I've got the integral 0 to b of e to the 8 minus s x dx, 1 over 8 minus s times e to the power 8 minus s x, oops, x. And there's no plus c here yet because I have to, slide. Ooh, what did I do? Run. Select. What?
You selected all.
They're selecting all sides.
Oh, I selected all slides. Oh, interesting. Edit. Oh, because I'm accidentally in that screen. All right, I'll get this right. Oh, there we go. Sorry, world, technical difficulties. Maybe we can switch pens. Select all, move over. All right. Switch pens. Where's the other magic pen? This. So I need to now evaluate that from 0 to b. All right, let's do that. So let's see. What's my variable of integration here? X is my variable of integration, yep. So everywhere there's an x, I'm going to replace it with a b. Well, there's only one x right there. So then I get 1 over 8 minus s. That's a constant. I'll just pull that out. So I get e to the 8 minus s times b minus e to the 8 minus s times 0. Okay, so I factored out the constants, and I only have to evaluate e to that power.
There's an s. There's 2 variables.
All right, so next thing to consider is I have to take the limit of that as b goes to infinity. So what is the limit as b goes to infinity of all of this stuff here? Now, I'm only working with b, and b only exists in this one spot. So technically, I can slide the limit all the way in there. Since there's no b here, what's the limit of that thing?
1 over 8 minus
It's just itself, yeah. So some things are just going to stay constant here. So I'm just going to kind of skip a step and say I'm going to get color 1 over 8 minus s pops out. And then I need to take the limit of e to the 8 minus s times b. And then the minus e to the other stuff, well, what's e to the 0?
1.
That's just 1. So that's just really 1 right there. So I only have to be concerned with that part right there. All right, so some other information back from the original problem about that. This is a Laplace transform. The definition is used to solve some important problems. The domain of f is the set of real numbers such that s such that the improper interval converges. So we got to figure out, well, when is this going to converge and when is it not going to converge? Well, if this is a positive number right here, and I go to infinity, that's a problem. Because if let's call that e to the a for a minute. If a is greater than 0, then e to the a looks like that. It increases forever. Okay. However, if that a is less than 0, then I get a decreasing exponential function, and that converges. Okay. So what that means is, in order for this to converge, we want 8 minus s to be less than 0. Okay. So if we solve that, I would add s to the other side. That means 8 has to be less than s, or you could say s is greater than 8. So if s is bigger than 8, right? Like what's a number bigger than 8?
8.1.
8.1, 9, 10, right? Then we're guaranteed a negative b as the power here. And as we go to infinity, then this exponential function is going to drop. Yeah. So here's my point. If this sucker right here is negative, well, that will be negative if s is greater than 8, right? Then I will get a decreasing exponential function as b goes to infinity.
How do you know that e converges? Is that the sentence?
Okay, good question. So let's just pick a number easier than e for a minute. So way back to Calc 1, think about 2 to the negative x. Okay, because I'm considering things like e to the negative x. Okay, and 2 is just easier to deal with. What does a negative exponent mean?
It's in the bottom over x.
Flip the base. So this becomes 1 over 2 to the x. Okay. What happens to 1 over 2 to the x?
No. Isn't it 2 over x?
So what's the base here? Sorry, I skipped a step. Okay. So negative means flip it. So that's 1 over 2 to the x, right? Negative exponent. Flip
Why
the base.
is 2 now in the denominator?
Because 2 is connected to the
Okay. What's the base here?
2.
Okay. So there's 2 in the denominator now.
Okay.
Just think of like 2, just don't think of x.
I
Think of
thought
x to
it
the
was
right.
1/2 to the negative x,
Yeah.
then 2.
It's negative.
Okay. So
No,
let's.
exponent is negative. So
Okay, I'll do this a slightly different way. What's the reciprocal of 2?
1/2.
So these two things are equal. This can also be written as 1 to the x over 2 to the x. What's 1 to the x always going to be? 1. And therefore, that's this right here.
Okay.
Okay, so what is x doing here?
Increasing.
Going to infinity, right? So if I plug in, say, 1 and then 10 and then 100, what's going to happen? Well, if I plug in 1, I get a half. If I plug in 10, I get 1 over 1024. if I plug in 100, I don't know what that is, 1/2 to the 100, which is a huge number in the denominator, which is going to be something like 0.00000 whatever.
So it goes.
Okay. So as x goes to infinity, this is going to 0. So as long as I can guarantee that exponent is negative for e, as x increases, the exponential is going to go to 0. With me?
So if it's going to 0, it's like converging.
So
It's
to
the same
converge means that you are heading toward a particular number.
So 0 counts as a particular number?
0 is a number.
God.
Yes.
But you can also say
So
it's not
okay.
line.
So review from Calc
We
1.
just are wrong.
What does it mean to converge? Converge means to approach a number.
Does 0 then count?
Well, you don't even
Okay.
need to think of
And
zero,
there are
you
lots
say
of numbers out there. 1 is a nice number to converge to. 0 is a number you can converge to. Pi could be converged to. 1/2. Square root of 2. 0.1234. Right?
Mhm.
What does it mean to not converge?
If you go from one side of the limit to the other
Okay.
side. you'll-
So to increase forever is not converging.
Something like sine. Like,
Yeah. Ever, yeah. Or oscillate.
Go back and forth.
Okay. So for example, if I took the limit as x goes to infinity of the natural log of x, the natural log x grows slowly, but it does grow forever. This does not exist. Now, normally we give a more specific answer than does not exist by saying it grows forever. Growing forever is a way of not existing. Alternatively, like Seiler said, if we tried to take the limit as n goes to or x goes to infinity of the sine of x, sine is always oscillating between -1 and 1, so this does not exist either. And I can't give a more specific than does not exist really, like I can't say infinity because it doesn't grow forever. I could say it lives between -1 and 1, but it still doesn't converge to anything. Yeah, so convergence means that as we look at a table of numbers, the answer is heading towards some real number. That real number could be 0. To diverge means it either grows forever to infinity, goes down to -infinity forever, or just never settles down, bounces around. And that's what it means to diverge. Yeah. So in this case, backing up to here, we've just established that if this exponent is negative, that means s has to be greater than 8. This sucker will go to 0. So back to my original problem. What's left? Well, this goes to 0. What's 0 minus 1?
-1.
-1. Okay, so the conclusion here is that this original integral at infinity is going to end up being equal to -1 over, let's see, what order did I write that?
A minus s?
8 minus s. I'd rather bring that negative into the bottom and say it's 1 over s minus 8. So this is what's called my Laplace transform function. The function e to the x in this alternate universe looks like 1 over s minus 8. So Laplace transforms take exponential functions and turn them into rational functions.
Oh.
So it's like a substitution kind of, it's a funky substitution. Yeah, like with our trig substitutions, we turn rational functions into trigonometric functions. A Laplace transform takes an exponential function and turns it into a rational function.
It does have to be exponential. Could it be a linear function too?
You can plug any function you want into a Laplace transform. And each class of function that we're familiar with in our universe turns into a different kind of function in the Laplace transform world.
So, like,
still can
they
test
don't spit out the same y values.
Correct. They do not spit out the same y values.
So then,
Yeah. Well, then what we do is we manipulate this in the Laplace transform world, and then we turn it back into our world function. Just like we do in trig substitution, right? We turn a rational function into a trig function,
and
then we turn it back into whatever, a regular function. Yeah.
Into another dimension.
So there are what are called inverse Laplace transforms. So what's the inverse Laplace transform of 1 over s minus 8?
E to the
It's
8x.
e to the 8x.
Oh my god.
You just like
And-
memorize them.
And those are, yeah, so just like we have tables of functions, like how do you take the antiderivative of this function? How do you take the antiderivative of that function? There's a whole book of Laplace Transform functions.
Are we gonna have to do some tests?
No,
Oh, sick.
well, it is an improper integral. You will have to do an improper integral on the test.
Wait, why did you say that?
But Laplace transforms are technically part of, usually they come up in differential equations and like sequence analysis, or, is that the right word? They come up in some engineering courses. I can't remember which ones. All right, let's do another problem. We got a few more minutes. What else do you want to do?
Let's go way back.
Go way back in calculus. Okay, in the way back machine, what looks exciting? Let's see, we did a Riemann sum yesterday. Oh, maybe we should do a fundamental theorem of calculus problem?
Yes.
Yeah.
Okay, let's do a fundamental theorem of calculus problem.
Still going over fundamental theory.
All right, let's see. According to the fundamental theorem of calculus, the FTC, let's call it, what would happen if we took the derivative with respect to x of the integral from 1 to x of the sine of t over t dt?
Wouldn't that wait?
It's sine t over t.
Sine of x over x minus, what's sine of 1?
If the sine
of
x,
t.
that's equal to sine
No,
x of
because
t.
the x replaces.
Oh, but yeah.
Boom, done.
That's it?
Yeah, the as long as this is an x up top there as the end boundary,
Why are you doing the derivative?
the derivative cancels the integral.
Okay, that's what I thought.
Yeah.
Wait.
To
we
put
just
in the
replace-
next size off.
We replace t with x.
Wait, so
That's
there
it.
can be any
Okay,
number
that's
on the
what I was
bottom?
Yep, let's do another one.
Hopefully there's like
It could be like
windows and
5.
ties.
Suppose we had the derivative with respect to x of the integral of pi over 2 to x of the sine of t squared dt.
It's sine of x squared.
That will be the sine of x squared.
Because the
I mean, these
derivative
problems are
cancels the
difficult.
pi over
Isn't
two.
there,
Now, what is that?
isn't there,
X? Upside down.
Okay,
Oh, the
let's
x
do a harder
squared.
one.
yeah, so that's-
Okay. Suppose we have the derivative with respect to x of the integral from 1 to x cubed of, let's make this one easier here, the sine of t dt.
Sine of x
It'd
cubed.
be
2x squared sine x cubed.
It'll be sine of x
Sine
cubed.
of x
So we got to plug in
3
the x cubed for t, but the chain rule says we need the derivative of that, so I'd have to multiply
2x.
somewhere by 3x squared. And you can put that out front or behind, but that would be it right there. Okay. Did that kind of happen in these problems here? Sort of. What's the derivative of x with respect to x?
1.
1. So I can multiply by a 1 there if I wanted.
We need to remember the definition.
The definition of the derivative?
Definition of the
Definite.
fundamental theorem of calculus, like and
Oh, am I going to make you state the definition like I did on
Okay,
test?
sorry.
I will
Any
not do that to you.
definitions. Any definitions?
I will not, no, because I'm giving you this cheat sheet of all the formulas and stuff.
just write it on.
So it makes writing definitions kind of moot.
Actually, you know what? On the take-home test, you just put one of those on.
Is that
Is
that
definitions.
I think we should run these up to.
Oh, I didn't reopen the wiki, but if you think, so what I'm going to give you, I'll send an email reminding you guys of this. What I'm going to give you for the test is the current version of the wiki with a couple of additions. The additions I was asked to put in there.
You were asked, like it's not you. It's just somebody else asked you. Do
So
we make?
yes, so this is, you're going to get an email that says this. So right now, we're going to have the integral table from the book. Integral table from the book
What's a book?
do you have a textbook?
website.
Thank you.
Okay, the former wiki that I gave you for the test, the cleaned up version.
Could I say
Let's see, what else? Rob gave me a suggestion. Oh, the volume pictures, the 4 different kinds of volumes.
Oh, amen.
Volume picture cheat sheets. The 3 trig substitution triangles.
We would do all basic derivatives. I agree.
It's gonna be a book.
Like the
No, I'll give you integral tables, but not derivative tables. Or I can give you derivative tables, but not integral.
Oh, no.
tables.
No,
Integral
he wants
tables,
to do
integral
integral
tables.
tables.
Wait, why?
But they're just backwards.
Yeah, I was
It's easy,
gonna
right?
say.
You have one, you have the other. Okay, so I'll send out an email saying, hey, is there anything else that should be there? And if you send me a request, I'll either respond with a yay or a nay.
Probably an ace.
So,
Somebody should
so
add-
derivative tables is a nay. I'm not putting derivative
Can
tables
we
and integral
put-
tables on there.
Well,
The linear, like just one of like the basic structure of the
Partial
quadratic partial fractions, like
Oh, partial fraction
Yeah.
change.
the
Can we put-
equation.
can we put the quadratic formula?
What?
No.
Trig identities? No, can we put trig
Well,
identities?
we
Yeah,
have some
because we
trig
got
identities
it.
on there already.
Really?
And we have
I swear
hyperbolic
to
trig
God, we
Do
use
we
identities.
have the ones that we need?
How long is this test?
I used it on one of the problems, I swear to God.
No more than 10 questions.
Is it gonna be?
For 2 hours?
Okay, well,
Is it gonna be no calculator?
there's gonna be a couple of questions. It's not gonna be all no calculator. I'll probably have a couple of questions where I say no calculator, but maybe not. I'm not done writing it. And then there'll be part of it where you definitely can use a calculator. One thing you cannot use is something like the integral calculator. That will be illegal for the test.
We can use decimals.
You can use it on the take-home test,
Oh,
but
Well,
not on the in-class test.
We can't check our stuff with the integral calculator?
On the
on the
take-home
test?
test, you can, but not on the test,
Why not?
because I said so.
so there's no calculators on the test.
I mean, we're still gonna have to show our work.
No, you can use a calculator on the test. You can't just use an integral calculator.
Don't be like, wait. But that's what's technically integrate.
Desmos only does numerical integration.
Yeah.
It doesn't give you the
do, like, the
spit
It
out.
doesn't give you exact values. And on the test, I'm gonna ask for exact values.
Okay, that's what I've just been.
So you can check to see if your exact values are close to GeoGebra's approximate value.
You just divide the answer by pi.
Yeah.
Don't that have more tricks?
Or square root of 2, or I mean, who knows what the constants are. It depends on the
It's
problem.
corrupt.
Okay, so I'll send an email with links to what I will give you for the test, asking if there's any other suggestions. I need that by Sunday night. I'll send an email out today, because I got a couple people that want to take the test in one day.
I mean, if you do it Monday, you don't have to come.
Yeah, and your deadline to take the test is with me at 10 o'clock on
Tuesday.
Thursday.
I have a track feed though.
Let's hope that's
our official
That's
time.
fine.
I think it's in the
we're gonna
calendar.
do it Wednesday, 'cause-
Is it in the calendar?
No, it's put on Wednesday. It's put on
No, but we'll have
Wednesday.
to-
Oh, I put it on Wednesday? Oh, yeah, that's because for the online people, I need them by
Because if
Wednesday.
it's 10 a.m. on Thursday, we'll be in class.
I think I might just like skip the rest of the day for Wednesday then.
All right, go forth.